Thank you. Previous slide. Okay. Okay, thank you. So as Rich said, I used to be in a lab called LIMC. I'm still there, but it has changed name. So it's called LISN now. So it's a lab of computational sciences, quite large, which is part of the University Paris-Saclay. Okay, but the work I will present today has been done mainly in collaboration with my former and current colleagues at KTH. So namely the team of Dan Henningson, Philipp Schlatter, and I will present also the work of two great PhD students. The former one was Taras Chapko, and the latest one, who's actually now a local in Cambridge, is in the room today, is Miguel Beneitez. Okay, so the question I want to address, the big question, the big motivation, is about the transition in incompressible shear flows. Here you have quet flow, here you have an instance of experimental boundary layer flows. And the question I'd like to ask general is, okay, how does localized turbulence proliferate spatially? So there are numerous ways to address this problem, either using statistical physics, but here we're interested in, you know, this individual protagonists here, there, which are turbulent spots, and we'd like to have a dynamical picture of how they arise. So for this, we would like to use our mathematical knowledge and have a dynamical system theory. So we know the Navier-Stokes equation, so I didn't write them entirely, but it's a PDE, that's what matters here. So formally, there's no problem turning this into a high-dimensional dynamical system, so with no spatial derivatives, only temporal ones, together with boundary conditions and initial conditions. So if we want to perform this change, of course, we have a few theoretical constraints. So the flows that I want to care about here, they're all characterized by most important properties that the laminar base flow, is usually an analytical solution, is linearly stable. But still, even if you linearize around it, you can, because of non-normal effects, there can still be a large amplification of initially small disturbances. There are other constraints, such as the conservation of energy by the nonlinear terms, etc. So what I will first illustrate the notion of edge state on a simple system, which verifies the properties of the previous slide, but clearly I killed a lot of modes here. So I'm using it's a toy system. It's the toy system of Dosho-Manville, and I could have used any other one for my purpose. But this is a two-dimensional ODE with here a linearly stable base flow, here a fixed point that is for today is my turbulent state. And if both are attracting, there must be something in between. That's the main idea. So there's between those two fixed points, there has to be an unstable fixed point, and it has a stable manifold in red here. So the stable manifold in red, I call it the edge manifold, and the attractor within that manifold is this unstable state XE, and this I call the edge state. Okay, it's important to know that the edge manifold itself, I call sigma, is the intersection between the closures of the basin of attraction of the turbulent state, and here the basin of attraction of the laminar state. So where they intersect, that defines our edge here. So here identifying that edge state is really easy. You solve for fixed points of that system. But if you have more degrees of freedom, like in your DNS computations, you need better methods, especially adapted to a high-dimensional system. So the usual method that we use is called bisection, or by some people shooting method. This is the edge manifold, and you're looking for that state. So what is important is to have in state space a line that crosses that manifold. that manifold has dimension n-1, so it's not difficult to find a line that crosses it. And then by refining the amplitude of the perturbation to the laminar flow, you try to stay on that edge. And naturally, if you do that for long enough and there's an attractor there, you will get it. So that's the standard numerical method to approach numerically edge states. I insist on the fact that the method is scalable, meaning that if you increase the dimension, it doesn't, the complexity doesn't rise. In the recent years, we actually thought about other alternative methods to find these edge states in general. So I will just illustrate them. The details can be found in this paper. So I use here the same toy system. And we found out that, for instance, if you plot the largest finite time Lyapunov exponents with varying time horizon, sorry, then something went wrong. Yeah, but yeah.
Mark, mute yourself.
Sorry. No.
Mark, mute yourself.
Maybe someone has the sound on, no? Okay. Okay, sounds much better now. I continue, okay? Sorry. Yeah, can everybody mute their microphones, please? Because we're getting feedback. Thank you. Oh, okay, let's continue and we'll see. Okay, so on the first plot here, we plotted the largest finite time Lyapunov exponents that can be found by using standard method. And you can see that actually it's maximal on the edge, not on the edge state particularly, but on the edge manifold. So that's a way, if you can compute this finite time Lyapunov exponents, to see the edge, especially in 2 dimensions. There are other indicators. So the trajectory length, sorry, I didn't put the formula, is just, well, actually the length between 2 points gets minimal on the edge manifold. So you don't see it really well here, but if you plot the gradient, then suddenly there's a singularity here. So it's another possible method to find edge and edge states, and they also resist well to increase in dimension. So we could use this with Navier-Stokes. And another method I briefly want to illustrate is a feedback control method that we developed with Ashley Willis and other people in Berlin. That's the uncontrolled system. So, well, that's another toy system. The edge is here. This is mu, stands for the Reynolds number. This is a stable fixed point, and this is our unstable fixed point that we want to stabilize. By adding a simple constraint, which is a linear relation between some amplitude and the Reynolds number, here we managed to stabilize the unstable fixed point. So that potentially can be a good idea. Okay, so that was a short one, but enough with toy systems. Now, who has done what with the Navier-Stokes equations? So here I'm reviewing, and I have obviously forgotten many names, what I think are the main steps in the identification of edge states in flows governed by the Navier-Stokes equation. So the simplest situation is when the edge state is obviously also a fixed point, yet in higher dimension. So for instance, that's the first edge state that was known, but it was not known as being part of the edge, was one of the unstable solutions found by Nagata in 1990 and rediscovered by many later. So it's called now the Nagata solution. It's a flow. The solution of the Navier-Stokes equation it's steady and it's unstable. So it has some instability. So maybe I didn't put the right one here. But this is actually a special case. Usually you get this by adding additional symmetries to the flow. If you simply take your DNS solver and apply the methods that I previously showed, what you find in general, it's my experience, is that the edge state has a chaotic dynamics. So, you know, you edge track, it never calms down to a steady state. So first, computation. So someone should mute the microphone again. Thank you. The first one in Navier-Stokes was found probably by Tobias Schneider, next speaker, and then we found many in other flows. Another property that I think is crucial for edge states, it's really crucial because it makes them physical objects, is that if you increase the domain size, at some point they start to localize. So that's the case of plane quasi-flow in the Tokoma and Barclay's tilted geometry. What matters is that in the end, we manage to converge to a localized state, and it's really localized in space. And this property is a robust one. So as soon as you do the bisection in large enough domains, you get localization. Okay. So we did that in other systems. So plane quad flow, for instance, as you see, this edge state as a chaotic dynamics looks like a turbulent spot. That's cylindrical pipe flow. In all those examples in large domains, if you do not apply special discrete symmetries, you do not find fixed points or periodic orbits. It's always chaotic in my experience. Okay. Okay, and briefly, there's a concept that I want to mention, but really briefly, that is connected with the notion of edge state, is the notion of minimal seed. So the minimal seed stands for, so in that state space, I come back to my toy system, is the least energetic perturbation at initial time. So for a given norm, usually energy norm. So typically, it's the here in that plot, it's that point, you know. I mean, if you consider turbulence as dangerous, then this is your, you know, your most dangerous perturbation. So that's for the toy system, but they using quite heavy adjoint methods. We can actually find them in the Navier-Stokes computations too. It's costly. So this is what the minimal seed. This is streamwise velocity perturbations, what the minimal seed looks, for instance, in plane quad flow, and this is how it scales, its energy scales with the Reynolds number. It decreases like a power law. Okay, so that gives us a state space picture. So here I so far I stick to wall-bounded flows with two walls at least, not boundary layers. This is what we would like to expect from a theory, you know. So here the laminar flow, here is our edge state, whatever its dynamical nature is the edge manifold, here's the minimal seed, and turbulence over there. So that's what we want to see. Note that it's not very different from the picture in the first edge state paper by Tony Itano. And this is what we get in simulations. Here's the minimal seed, the edge state we found to be chaotic, and this is how trajectory escape from the edge to reach turbulence. Okay. So that's a nice picture, but okay, now can we extend it to boundary layer flows? And so first I would like to distinguish between two types of boundary layer flows. Of course, the one we would like to tackle is the spatially developing boundary layer. So here, Blasius. Yet you can also consider parallel boundary layers. I will start with this because the transition is smoother. So the flow I would like to consider is the asymptotic suction boundary layer. Is the same flow except that you can apply suction at the wall, and that prevents the boundary layer from growing. So asymptotically speaking, it's a parallel flow. So this is the easy case because I'll tell you the answer. Technically, it works like plane quad flow or plane quasi flow. It's quite close to plane quasi actually, except that there's no roof. So this, okay, that's a large computation of, that's not the edge, it's turbulence. This is how the laminar flow looks like, and it's linearly stable until very high Reynolds numbers. So we can apply the classical bisection. And then we did that first in boxes that were wide enough, and we find a localized edge state. That's not surprising. We find an interesting dynamics where actually you have two low speed streaks this is streamwise velocity, in blue sandwiching a high speed streak in red, and through some kind of cycle, at some point you see that it has moved sideways. So the mechanism is quite complicated. So the streamwise vortices do cross, and so lift up gets inverted, and low speed streaks become high speed streaks, and that results in an apparent side shift. And we could find actually several edge states, a finite number of them, depending on whether the side shift occurred to the left, to the right, left and right, or in a chaotic way. Okay. So this is the system is still constrained in the streamwise direction. Now, if you do not constrain it, and we make the domain as large as we could, so now it becomes costly. You see, we needed the help of praise. So here I'm displaying blue and red are still streamwise velocity isocontours, and green is the lambda 2 criterion. So here is a video of the dynamics. So you see that this shifts sideways, you get this streak switching, and at the end, we do not edge track until the end. Now we're not on the edge anymore, and it transitions and makes a huge spot, and we have to stop the simulation. Okay? So interestingly, this kind of initial structure can be recognized also in, I would say, turbulent simulation, not fully turbulent, but so here is still the same flow, except the initial condition is just noise with no particular amplitude. And so what happens is that the noise quickly dissipates, and locally you get seeds for transition through turbulent spots. And so let me show it again. Now look at these times now. I will show it on other pictures. This is the edge state as we computed it using bisection, and these are our pre-nucleation event, and they are really similar also in amplitude, streak width, etc. And this is a projection in a two-dimensional state portrait where we see here the edge. Here are a lot of noisy initial condition, and you see that before it swings off to turbulence, it locally approaches the edge state. Of course, it's a two-dimensional phase portrait. It can hide things, but so it gives an importance to edge states in natural transitional flows. So it's not only a theoretical view of the mind, I think. Now we can move on to the Blasius boundary layer. So the story and the motivations are the same, but the spatial development has some difficult implications, especially for the theoretical point of view. So of course, we're still interested in edge state as precursor of turbulent spots. So we did a few bisections, but they're all costly because we need to consider very long domains. The domains are periodic, but there's a fringe at the end to kill the outgoing perturbations. So one of the main problems, we know it, and it was also the case in plane quasi flow, by the way, but nobody mentions it, is that this flow is known to be unstable. And at the beginning, I said, oh yeah, we need a linearly stable base flow, but a Blasius flow will eventually always develop Thormian-Schlichting waves. We know it, okay? So yet here in this paper in 2012, we had no problem bisecting, and we didn't see traveling waves. So we started from an initial condition that was spanwise symmetric, and it has a complicated dynamics. Essentially, it's a pair of streaks, with perturbations that grow here and overtake the main structure. So snapshots. These are state portraits based on some energetical variables. So that's what we did with the symmetric initial condition. And then later we restarted with a non-symmetric initial condition with Miguel Beneitez. And importantly, we went further. Thank you, Rich. We went much further in time. And then we saw the possibility for Tolmien-Schlichting waves appearing. So you see, these are sandwich trajectories that sandwich the edge, and this one is above the edge, goes to turbulence, and this one is below, but still goes to turbulence. So where is the edge? There's an interpretation problem here, and actually we reinterpreted our edge trajectory not as being on the boundary between the laminar and turbulent basins, but between two types of transition. One is the bypass transition, is the above one, it features streaks, and the other one is the expected one from classical theory that involves Tolmien-Schlichting waves, okay? So it's quite complicated. Then this is the original paper of Markovi in 1969, and this is the sketch he did. And you see that it's complicated, but not less complicated than the sketch itself. Interestingly, we looked at the dynamics of this edge state, and we also saw streak switching appearing in the same way, but not so many events, in fact. So that has implications. Because the TS waves appear at some point, you cannot perform a bisection beyond a finite time. So is that time short or not? So if we look at, for instance, bypass transition, the experimental transition location as a function of the turbulence level, then you will see that, so we can cite edge track until more or less that distance, which corresponds compared to the experiments to a level of turbulence of 1 to 2%. So it means that above that, for more than 2% turbulence, the edge state can be computed. So you can use it to do stability analysis and see precursors of turbulent spots. There's a gray zone, and below 1%, it's not a surprise for people who know wind tunnels, classical transition dominates, and it will be very difficult to make any sense of this edge concept. Okay, okay, I'll be quick now. We wanted to understand better how this edge concept could be destroyed by the existence of unstable modes. So here is our toy system again. Then what we did is that we added one equation corresponding to the additional instability of TS waves. And of course, we care that the energy is conserved. So what we found, so the original Dorsho-Manville system, it lies in the 2D plane here. And as you increase this new parameter S3, you create an additional state that then is quite complicated, grows, collides with the original edge. But the edge state is still accessible by bisection. And then this new state S collides with the plane. So, and then it's non-accessible by bisection. So the edge state still exists, but it's no longer an edge state. That's the idea. Okay. And in the 3 slides, what we are currently trying to do now is to linearize around the unstable edge trajectory. So that's the one that we're considering that is actually initiated by the minimal seed. So now we have a time-dependent base flow. So it's quite difficult to try to extract information from that. Can discuss later in private. This is as time goes, how the eigenvalue, instantaneous eigenvalues change along the flow. And you see this is the numerical abscissa versus time. You see that you have instances of non-normality, especially not initially, but in the first phase. We're trying to understand that, compute finite time Lyapunov exponents, distributions, and try to understand what the leading instantaneous eigenmodes can be, to see whether there are some phases of the edge states that are more unstable than others. Okay, so you said 25 minutes. I'm there. Pure luck. So here are my conclusions. So, okay, it's possible, at least first in wall-bounded flows, to have a deterministic picture that is robust when you go to large domains. That's important. So edge states are physical objects, despite the fact that they're unstable. Their dynamics is usually complex, and okay, especially boundary layer flows, there's a time limitation. So you cannot do linear stability analysis. It has to be finite time linear stability analysis. And the work in progress is precisely this. Okay, and then with that, I'd like to thank you. Really?
Thank you for the beautiful talk. I have a question about the Couette flow and the finding the footprint of the edge state in the transition. Is the question how long you see it? Because if you're going from laminar to turbulent, you have to cross that, don't you? So how long does it?
No, you don't cross the edge. You can't cross a stable manifold. You're on one side or on the other one, and then it might be very convoluted, but you do not cross the edge. It's important.
So you're getting close to it and coming back again.
Yes.
But the question is how long do you sit close to that?
Yeah. So are you talking about the transient?
Yeah, it was the Couette one where you showed
quite
the streaks.
quick. Yeah. It's quite quick. I mean, should I answer in time units or something like 100 time units?
Okay.
But you mean that's no, not this.
Yeah, you had a comparison
here,
a static picture with where you showed side by side the.
No, sorry, this one.
Yeah, that one.
Yeah, here.
So the bottom. Yeah.
That approach, that's ISBL, not quite, by the way. The time of approach here, we
oh, that's the plot.
Yeah, well, that's quite long actually, but
yeah, that's the answer to my question. So it
in an
hangs around for
experiment,
a
you
while.
would be very rapid. I mean,
well,
that's what.
Okay, that's the other question. Can we observe that? Yeah.
In DNS, you can take your time to analyze, but in experiments, I doubt you can really see it in all cases.
Thank you.
Young?
Yeah, I think Yohann. Yes, I was quite interested in the way that you calculate the edge by computing Lyapunov exponent.
Yes.
I guess that doesn't work for turbulent to flow. If you really apply that technique to the Navier-Stokes, because in your model system, you have two attractors. They are stable, so therefore the expectation is that these guys have a small. Yes, this one, first one.
Yes.
Do you think this is going to work in Navier-Stokes?
We did it.
Oh, you did it?
Yeah, okay. We did it with Miguel. We tried to find the edge state rather than using that classical bisection by, it's still a bisection, but not based on energy levels, but based on, the value of a finite time Lyapunov exponent, the largest one. And we could find the edge state again by using this in a small box of Couette flow.
Then my question is that the finite time Lyapunov exponent on the edge is always greater than that of the turbulent state.
I don't think so.
Okay.
No, I don't think. But the turbulent state is far from there. But locally, it's a local maximum. I didn't compare. I mean, we didn't compare with whatever was around the turbulent.
Okay, that's fine then. Yeah.
Yes.
Right. When you have the breakdown of the stringwise vortices and the string, you see hairpins. What happened with hairpins in your model? Because
in which flow?
In the last, which you have, by example, two quickly stringwise vortex and red and one in blue, and after you have.
Yeah, well, you should tell me which flow you have in mind.
Modernized, I think. More.
Here?
Yes, perhaps.
Yeah. In this flow, we see hairpin vortices, but this is because that case, there's an initial condition which is spanwise symmetric. And then when we didn't make it spanwise, so if you see that video again, you will see hairpin vortices. You see here, somewhere there. But if you don't impose this symmetry, like Yeah, like that. Sorry, don't see the same thing here. In that case, we didn't see many.
In the Blasius case, where you introduce,
Sorry, it will be difficult.
where you introduced starting with the random, it's the video you just showed a couple of times. At the beginning, it seems to contain. Started again. It looks like, could it be competing with other modes like K-type and H-type mode of instability?
This is ASBL, and this the TS waves. They I mean, this is Reynolds 500, if I remember well. They are not unstable before 75,000. So I don't think so. It's because the numbers do not fit well.
I see, because it seems there are some clear oblique initially.
Should watch it again.
Right at the beginning.
It's probably due to the structures that are in the noise. I wouldn't interpret them physically.
Is there bad? You want to move?
So congrats to your exciting talk. So what type of results do you think you can present about 10 years down the road? I mean, what type of simplification or mathematical theory or phenomenology do you want to achieve, let's say, in the next 10 years down the road?
Well, me, I don't know, but if in 10 years you give a talk about control using edge states, I'll be really happy. It's true.
Okay.
Yeah.